Let's look at x first. Look at the larger number and identify what it is. This is a positive 4x. So what do I wish this was? A negative 4x. Right? So you always look at the larger number, say what it is, positive or negative. Positive 4x, I wish this was a negative 4x. And how do I turn it into a negative 4x? Multiply by 2. Okay, and that's it. So I multiply that whole top equation. Watch me write my distribution lines. So it's negative 4x plus 4y equals 20. I draw my distribution lines because the most common mistake I and other people make is to not distribute the 2 all the way over to the 10, which Hector correctly pointed out to me a while ago that that's not real distribution. You're technically multiplying the left-hand side by 2 and you're multiplying the right-hand side by 2. So that's like the lazy person's distribution, right? But the point is you're multiplying everything by 2, just like before we multiplied everything by negative 1, or we changed all the signs. Okay, so did we accomplish it? There was a positive 4x, now there's a negative 4x, and now we can do elimination. So again, we'll just do the elimination step. That leaves me with 1y equals 9. Do I even have to write the 1? No, I can just say y equals 9. Okay, so that's the elimination step. We're just practicing the elimination step. Let's pretend we had wanted to eliminate the y variable. So what do? You look at the bigger number, so negative 3. You say this is a negative 3y. I wish this was a positive 3y. Is there an easy way to turn that into a positive 3? Positive 3? Well, we want to turn it into a positive 3. Like here, to turn that into a 4, we just had to multiply by 2. That was very easy. But can I turn a 2 into a 3?
You're gonna have
That's what we'll do next. But is there one number I can multiply times 2 to make it equal 3? Well, I mean, there is, but it's a fraction.
Yeah.
Nobody wants to do that.
I was thinking 3 over 2.
Yeah, that's correct. It'd be the fraction 3/2, or just the number 1.5. But nobody wants to think in terms of fractions or decimals. And so given the choice between eliminating x and eliminating y, you would just eliminate x, because that was the easier choice. Let's look over here. We have 2 choices. We can eliminate the x variable, or we can eliminate the y variable. Let's look at the x variable first. Look at the larger number. So that's a negative 6x. What do I wish this was? A positive 6x. Can I turn it into a positive 6x? Multiply by negative 2. Yep. So let's do it. Let's go and distribute that all the way across. So that gives us positive 6x. Now you notice how important it is that you write the positive 6x. I know we go through life that if you just write the number 6, it is assumed to be positive. But right now it's very helpful that every number has an actual sign in front of it. So don't just write 6, write positive 6, because that's all the more clear to your brain and your audience that these 2 numbers are going to cancel out. So then minus 20y equals positive 56. Okay, so we eliminate the x variable, and we get negative 18y equals 72. We divide by negative 18, we get y equals negative 4. And we're about to show you something, which I think is what makes elimination so cool. Okay, so I just wrote it again. You'll have to too. So we just did elimination to solve for y. So how would we solve for x? You plug y into one of those and you solve for x, right? Now just watch. I mean, if you did do that, I'm just going to go ahead and choose the first one. So negative 3x plus 10y equals negative 28. So then I would go ahead and plug in the negative 4. So it'd be negative 3x plus 10 times negative 4. And then I would multiply that, and then I'd have negative 3x minus 40, so negative 28. Then I'd move the 40 over, and then I'd have something, negative 3x equals 12, and then I'd divide up to negative 3, and then I would get my x equals negative 4. Okay. That's all well and good. That's perfectly fine, and that's using substitution to solve for the other variable. So you notice that traditionally, we do elimination to solve for one variable, and then substitution to solve for the other variable. But you could just do substitution twice. I'm sorry, elimination twice. You could just do elimination twice. So what did we just eliminate? X. So now let's eliminate y. Okay, now look at y. So look at the larger number, positive 10y. What do I wish this were? Negative 10y. Can I make that a negative 10? What do I multiply by? Negative 5. So now I distribute that all the way across, and I get 30x minus 10y equals negative 80. I'm going to rewrite the top equation down here below it because it's no good for my eyeball to have to go up and down that far. So negative 3x plus 10y equals negative 28. And now I'm ready to eliminate y. Isn't this fun? So you can just manipulate, not your friends, equations, and eliminate one variable and then the other variable. So eliminate the y variable, I have 27x equals negative 108 divided by 27. You get x equals something. I think that's a negative. Hey, which happens to be the same number I got out of substitution. Now, to be honest, you know, the amount of work I did doing substitution versus the amount of work I did doing elimination, maybe it's same.
I think it's better to just substitute.
Yeah, maybe just substitution is fine. It's totally up to you. There will be questions on the test where I say solve this one using elimination, solve this one using substitution. But if I say solve it with elimination, all that really means is show me the first elimination. And then you can solve the second variable however you wish. Okay, so apparently the answer is negative 4. Do we think we're right? Yeah, plug it back in. I don't know if we're right or wrong. We could have made a lot of mistakes. So I'm going to plug in negative 4, plug in negative 4. So now that's 12 minus 40. That does equal negative 28. And then here, 24 minus 8. That does equal 16. So good. It works. Now, all the elimination problems we've done so far were pretty easy because it was simple to find a number that you could multiply to create a situation where one variable had the same number but opposite signs. So let's see, isn't there a problem maybe right down below where it's not easy to find? Oh no, all those are easy as well. There will be some in the regular packet. Sometimes you have to multiply both equations by a number in order to get a variable to eliminate. Yeah, that'd be the greatest comeback. Okay, folks, you're doing great. We are going to solve this wonderful word problem. Now, at the beginning of class, we did a word problem about the animals in the barn. And I talked about how to convert a word problem into an algebra problem. What was step 1? Find the variables. And what was step 2? Create the equations. Very good. Create or write, however you want to say that. Okay. Now, to be fair, folks, see, the sheer ability to just look at a word problem and then define the variables and then make the equations, that's a skill in and of itself. That's a challenging skill to learn in and of itself, is just how to know what should my variables be and what are the equations I'm dealing with, let alone then solving the equations, which is algebra, right? So there's a lot of rich structure here that you have to learn. Okay, but the first thing you do is just read the problem. And I always try to read a problem in an attitude of silliness. I don't know how well that always goes for everybody, but see, I think a lot of word problems are very silly or interesting, you know? So let's start. The school that Elisa goes to is selling tickets to a play. Presumably the children are the actors, right? Guessing. On the first day of ticket sales, the school sold 12 senior citizen tickets and 3 child tickets for a total of $81. So folks, who are we selling tickets to? Old people and toddlers. Who's attending this play?
Old people.
Old people and toddlers. It's an interesting audience. You know, I don't know how that's going to work. I don't know if they make all the toddlers sit over here and all the old people sit over here. Here are the people who are our age. Not at this play. Okay, 20-year-olds, 30-year-olds, 40-year-olds, not allowed in. Okay, this play is for old people and toddlers. Does anyone know what this play would be?
Ask your dad.
Hamlet.
Yeah, Hamlet. Yeah, do you think Hamlet? Yeah, I'm. You know, what would a play be that's only interesting to older people?
Disney.
Disney?
I don't know.
Oh wait, The Lion King.
Maybe The Lion King? Yeah, I just don't know. Yeah, it's tough to say. Okay, so moving on. The school took in $65 on the second day by selling 6 senior citizen tickets and 5 child tickets. Okay, so next question, just to be silly. Does this mean that that's how many actually attended the play that day? Like on the first day, Did they have the whole play and the only people that showed up was 10 oldies and 3 toddlers, and that the school put on a performance for just 15 people? No, these are just ticket sales, right?
So let's see, wait, I'm gonna assume that one oldie came with their, I'm gonna assume that one oldie came with their toddler, the 3 toddlers, the other 3 just.
Yeah, how does this even work? The toddlers didn't come by themselves, so, presumably, maybe just one old person brought 3 toddlers, and then 11 old people all came by themselves. You never know, right? So there's a lot to think about here. This could be a sitcom, maybe. Okay, so finally, what is the price of each senior citizen ticket and one child ticket? Okay, so step 1 is define the variables. Now, where do we go to look to find variables? At the question. So the question at the end will always tell you what the variables should represent, and the question says, what is the price of a senior citizen ticket, and what is the price of a child ticket? So we say, let X equal what? X will be the question is, what is the price of a senior citizen ticket, and what is the price of a child ticket? So are we going to let X be? Sure, what about the senior ticket? Right, and the word they're using? Look at the question itself. What is the price? So let X equal the price. We try to use the same language as much as possible, right? You just steal the language right from the question. So X is the price of senior citizen ticket. I could just call that a senior ticket. So yeah, we try to use the same language from the question to keep it as clear as possible. So X is the price of the senior ticket, and therefore Y is the price of the toddler ticket or the child ticket. Very good. We totally have time to finish this question. We're doing it. Okay, so there we just defined our variables. We got those variables straight from the question at the end, and we use the same verbiage. Okay, so now what equations do we write down? We have to go back and look at the information they gave us. Very good. Gabe just shouted out 12x plus 3y equals 81. Now, first of all, did we get those variables straight? Does x represent seniors? Yeah. Does y represent children? Okay. Is this equation correct? What is this equation correct? 81 what? Yeah. That 81 is $1, right? Is the 12 $1? What's the 12? Yeah, that's the number of tickets in seniors. What did x represent again? The price of it. So 12 times that, together that equals a price. And then again, does 3 represent a price? No, that's the total number of children. Okay, so great, there's one equation. What's the next equation? 6x plus 5y. Does everybody agree? Is that the second equation? Yeah, looks like it. Okay, well there we go. As I said, that's one skill in and of itself. You read the problem, you turn it into variables, you turn it into equations. Now you're ready to begin. Now how could you solve this thing? You could graph it by typing it into Desmos. You could do systematic guessing and just start guessing about the price of the tickets. You could do substitution, which would be unfortunate because none of the coefficients are 1. So no substitution. What elimination we could do? Now folks, we've already done the easiness of something like eliminating x, right? Because this is a positive 12x. Can we turn that into a negative 12x? Very easily. So let's not do the easy one, and let's try eliminating y. Okay, so let's look at y. So the bigger number is positive 5y. Can I turn 3 into a 5? No. But what do 3 and 5 both go into? 15. So if you were looking at fractions like 1/3 and 1/5, what would be the common denominator? What?
I was going to say that you could multiply the bottom equation by negative 2.
Negative 3, and then the top equation by 5. That'll be correct. Well, let's just finish this one. The common denominator would be 15. So I multiply this by 5 to create a 15 down here, and this by 3 to create a 15 down here. And that way I have 5/15ths. Oops. 5/15ths plus 3/15ths. And now I have a common denominator. I want this to be the same number. So if I multiply the top by 5, which is really just the bottom number's coefficient, and I multiply the bottom by 3, which is really just the top, equation's coefficient. At that point, I would have 15y and 15y. But I need one of them to be negative. So which one do you want to make negative? Doesn't matter. Doesn't matter. You choose, right? So I'll go ahead and make what? The bottom one? Sure. Okay. So I'm gonna bring my work over here. It would be much better if I could just work straight down. So now we distribute all the way. Make sure you distribute all the way because that's the biggest mistake is not to distribute all the way. So multiplying the 5, we get 60x plus 15y equals 405. And then multiplying the negative 3, we get negative 18x minus 15y equals negative 195. Now I'll leave it to you to tell me if I did that right. I hope. So, did we create a situation in which the y variable will cancel? Yeah, we sure did. Isn't that interesting? You see, that's a pure act of creation on your part. It's just decision making on your part. Which variable do I want to eliminate? How am I going to do it? So we eliminate the y variables, and we now have 42x equals 405 minus 190. Is that 210? That seems right. Divide up 42. We get x equals 5. Now here comes the big question and why we did the work early on. What is that 5? Is that 5 old people, 5 toddlers, the cost of an old person ticket, or the cost of a toddler ticket? What does that 5 mean? How do you know? Because you wrote it down. Isn't that nice of you that your past self wrote it down so that you wouldn't have to think about it later? We know exactly what that 5 means. It's the price of the senior ticket. So now I just go and write a dollar sign. I write $5 per senior. How valuable is it that we define our variables in the beginning? It's very valuable. Because otherwise it's so easy to lose track of what on earth you were solving. Yeah, that's why it is going to be a blockbuster. Okay, now how do we solve for y? Just plug it into whatever you want. You can do elimination. You know, we were saying that it would be pretty easy to eliminate the x variable. Now that we did the harder one, maybe it would make more sense because I'm just going to multiply by -2, and that would be negative 12x minus ny equals negative 130. That way my x's cancel out, and I have negative 8y equals 15. Yeah. Oh, 81 minus 130, that'd be negative 200. What? No,
it should be negative 49.
Negative 49? What did I do wrong? Oh, that's a 7. There we go. That makes more sense. So, and then divide by -7, and y is? No, y is 7. 7 what? 7 old people, 7 toddlers, 7 the cost of an old person's ticket, the cost of a toddler ticket. It's just the price of child. So it's $7 per child.
That kind of blows.
You know, look at that. Who are we charging more for? The toddler, but that probably makes sense because toddlers, they put snot all over everything. They're rambunctious, they run around. You have to tell them to be quiet. I'm just being funny, guys.
So you're paying more for that thing.
Yeah, you're paying more for the child. Maybe the child seats are more costly because there are seatbelts and straps to hold them down. I don't know. Well, folks.
An IV with elephant equalizer.
Yeah, exactly. Okay, well, folks, you did great today. We covered a lot of good material. We talked about substitution, elimination, graphing, and systematic guessing. And next time you come back, we'll start in with our regular note packet that I'll collect for a grade. We'll do all that and then move on to our matrix operations.
So for our homework,
Oh, right, because today's Wednesday. Nothing is due on.
Monday,
Oh, I don't think so. Yeah, because
we didn't get to cover that.
yeah, we didn't cover it. So I would say no. Nothing is due on Monday. Thanks for asking. Lee, once again, thank you.